We continue characterizing stars, and this time we're going to be looking at the masses of stars. It is difficult to determine the mass of a single star, but it can be done for binary systems. The big questions are, what are the masses of stars? Is mass related to luminosity? Well, it turns out that mass can only be determined if we know how it affects another body that we can observe. And luckily, there are some binary stars that we can see and use to determine the masses. So, what are binary stars? Well, a binary star is a system of two stars, one orbiting another one, and we can see it here. And this comes from the Mizra system, and it shows a series of pictures taken between May 2 and June 4 of 1996. Again, it's the system Mizra, and the separation is a tiny angle, 0.01 arc seconds. Luckily, there are a large number of binary systems. About 1/3 of the stars that we can get to see in the Milky Way are double stars. Binary systems are two stars that are bound to each other. They are orbiting one another. Of course, there are some cases in which we see two stars nearby, but they are not bound. In this case, they are known as optical doubles, and they are just stars that happen to be in the line of sight near one another, but one can be farther than the other one and they are not bound. If in a binary system we can get to see that both stars, then that system is known as a visual binary. And if we can map the trajectories of the two stars, then we can determine the masses. This can be done by using Kepler's third law, which is the same that was used to determine the masses of planets around the Sun. And it turns out that if we know the geometry of the trajectories, then we can use this relationship to determine the mass of the combined system. By looking at in this case we have two stars, one say red, one blue. If we sit on the red one, we're going to see the blue one orbit around the red one like this. And if we sit on the blue one, we're going to see the red one orbiting the blue one like this. In both cases, the trajectories are ellipses. And the ellipses are characterized by this distance from the center to the edge. And this would be the semi-major axis, which we call A, letter A. And if we see the period, how long it takes for one star to complete an orbit around the other one, then that would be called the period. And if we measure it in years, then this rule applies, that the semi-major axis to the third power divided by the period to the second power will give you the sum of the two masses of the two stars in solar masses. One example, suppose that we have two stars in a binary system, and one we can determine the elliptical semi-major axis to be 4 astronomical units and the period to be 2.5 years. Then what is the total mass of the system? Well, it's simply 4 to the third power divided by 2.5 to the second power, and doing the operation we get 10.2 solar masses. Now this is the combined mass of these two. There is no way in which we can tell which one is what are the individual masses. Here we have one of those cases, and this is orbiting behind, and then it passes in front of the other star. This video shows how the one star, by passing in front of the other one, eclipses it. In other words, by going in front or behind, it changes the luminosity. So we can see the brightness here that we receive here from Earth as a function of time, and as one star goes around the other one, the intensity will vary. The maximum being when they are side by side. So here they are side by side, here they are side by side, the same here. But in one case, one is going to be behind the other one, and we're going to see only the light of one, which is less than the combined light, so we're going to see a dip. And when the other one is in front, then it will be obscuring part of it, and we're going to have a larger dip. Let's look at this video. We have different cases depending on the overlap between the two stars. We can see here that in this case the yellow star passes in front of the blue star, but it does not obscure it completely, so this is known as a partial eclipse. And in this case we have one larger star and a smaller star, and the smaller star is passing in front of it, and it is a total eclipse in the sense that it's fully embedded in the in front of the larger star. And in this case, it will take some time for the smaller star to go from one edge to the other edge. So in that case, the light, the amount of light that we're seeing, drops and then stays constant for the time during which this blue star is fully embedded on the orange star. We have another case here. In this case, it was taken by a camera that was moved for the duration of the eclipse. So we see here both stars shining, and then one being in front of the other one, and the one in front is much dimmer than the one behind. So it is eclipsing it, dropping the intensity almost to zero, and then it goes back to normal again. So we have partial eclipse, total eclipse, and this is the binary NN serpents. Now for this, I want you to please go to your lecture tutorial booklet in page 121 and look at the case of the exercise of binary stars. In this exercise, you will learn about eclipsing binary stars, and you're going to learn about the amount of light that we perceive at different stages of the eclipse. And I want you to please pause this video, do the exercise, spend say like 15 minutes doing it, and then come back to check your answers. Okay, let's start with the pre-activity question. For which of these, we have 5 cases here, for which binary star system made out of 2 main sequence stars an Earth observer would detect the least amount of total light. Let me start with the last one. We have a star with absolute magnitude 5 behind the star with an absolute magnitude of -2. Well, here, if this one is behind this one, then this is much brighter, so we're going to see a lot of light. In this case, the 5 is in front of a 1, so this is dimmer. It will be reducing the intensity of this one because it's in front, so this is going to be dimmer than this one. A 5 behind the star of 1, well, it is again, it will be behind the 1, so we're going to see the brightness of the 1, which in this case is brighter than this case. A 1 behind the star of absolute magnitude of 2, and here, it being behind, we're going to see the brightness of a 2, which is the same as in this case. It is the brightness of 2. But here we have a 5 in front of a -2, so this 5 being dimmer will reduce the total intensity of the system, and instead of looking at -2, we're going to see perhaps part of -2 and all of it, of a 5. So it's going to be way less light than in the other cases. So the answer is A. But if we, depending on the sizes, here, in this case, we're going to see 5 in front of a 2. If 5 is as large as 2, then we're going to see nothing but intensity of a 5. And here, if 5 is of the same size of 1, we're going to see exactly the same intensity as before, the intensity of a 5. So depending on the relative sizes of the stars, we're going to see different things. But in all of the 5 cases, these 2 are the ones that will produce the least amount of light. On question number 2, when would you receive the greatest amount of light from a binary system consisting of an M5 red giant and an M5 main sequence? Well, being both M5s, we know that they have the same spectral, they are of the same spectral class, they have the same temperature, and so we see that part A, when the red giant is in front of the main sequence, when the main sequence is in front of the red giant, and we should receive the same. Well, it turns out that the answer is C, and to understand that, we have to see the H&R diagram. We have both M5 stars have similar temperatures but different luminosity. M5 is around here. This is a main sequence, and this is a red giant. And this is much larger than this one, which is extremely small. This is about less than 1/10 of the radius of the sun, and this is about almost 100 times the radius of the sun. So having this one in front of that one will obscure almost nothing the red giant, because the diameter of the red giant is about 1,000 times that of the main sequence star. Point 1, question 1. Imagine that we measure the light emitted by a sun-like main sequence star during several weeks, 3 weeks. Which of the graphs most likely shows the brightness versus time This is brightness, this is time. In this case, we see that as time goes on, it gets brighter and brighter. The star would get brighter and brighter. And in this case, it stays constant. Well, the answer is easy. All we have to do is just look at our own sun. The brightness does not change as a function of time. So the answer is B. Question number 2. It says, imagine that instead we measure the light emitted by an A spectral type main sequence star at the same distance as the sun, the same distance as the sun from question 1, for again 3 weeks. Compared to the graph of the sun star light you showed above, which is this one here, which of these two would show the brightness of versus time for the A spectral type star? Well, in this case, our sun, we concluded that it should be producing, say, 1 and a fraction, say 1.5 units of brightness. In this case, we have 1, 2.5. In this case, we have about half. So this is dimmer than our sun. This is brighter than our sun. Being that this is an A-type main sequence star, means that it's larger, hotter, so it is going to be brighter. So this is going to be the answer. Question number 3. Imagine that these two stars, and we're talking about the one brighter than the sun and the sun, imagine they are actually quite close, so that the total amount of light received can be shown in a single graph. In other words, we're going to be adding these two intensities. Which of these two graphs most likely shows the combined graph of the brightness versus time? Well, this is 1, 2.5. This is 1.5, so it's going to be something like around 4. So in this case, it's going to be 1, 2, 3, 4. That one. This one is only 2.5, so it's the same as this solar star. So the answer is going to be A, E. The brightnesses add up. Number 4. Imagine that these two stars represent a sun-like in an A spectral type star. Label which object would represent the sun and which would represent the A spectral type star. Well, if we remember the shape of the snake representing the main sequence stars in the H&R diagram, we see that as we move towards the A side of the spectrum, the stars become larger. So this would be the A, and this would be the sun-like star, the G. Question number 5. The stars that are very close together will orbit around each other, and they will produce this type of fluctuation of the brightness as a function of time. And which of the two times, we have two times labeled here, time 1 and time 2, most likely indicates the time when the sun was passing in front of the A spectral type star. Well, this is less bright than this one, so if it's in front, the brightness of this one would drop, and again the brightness of the combined system would drop. So we have here the combined system, combined system, combined system, and here we have a dip, we have another dip. Of course, if G is behind, we're going to see nothing but the A, which is very bright. So it's going to dip a little, but not as much as in this case, in which G is replacing part of A by being inside, replacing part of A. So we're going to see not all of A, but A minus the area covered by G plus the brightness of G, which is going to be this one here. So we have here A in front obscuring G, A and G both visible, and here G in front of A. Question 6. What is the physical reason the bottom of the dip is a horizontal line rather than a point? Well, we saw this before. It has to do with the fact that one of the stars is smaller than the other one, like in this case. The brightness, the combined brightness of both systems here is the same as here. So the fact that it's flat indicates that the star is smaller and it will be embedded fully into the larger one. Question number 7. Imagine that you're watching a binary star system containing an M and a B, and during this time you're able to see the stars entirely separate from one another. At another time you see the B in front of the M, and at another time you see the B, it's moved behind the M. In the spaces below, draw 3 sketches showing how the stars would look at the 3 times. Well, it is simply the stars. One is going to be a B, is much larger than the other one, which is an M. Both of them main sequence, so we see that the B is going to be much brighter than the M, and also is going to be larger. And we can see that the M is around a few tenths of the radius of the sun, and the B is several times larger than the radius of the sun. So one is large, the other one's small. So the drawing should look like something like this. This is 2 side by side, one behind, the M behind, and the M in front. Question 8. At which of these 3 times would you measure the greatest amount of light? Well, it is clear that in this case we would see the largest amount of light because it is the brightness of M is added to the brightness of B. But for the question number 9, at which of these 3 times would you measure the least amount of light? Well, in this case, because in this case M is taking a little bit of the B brightness and replacing it by an M, which is much dimmer. So it's when M is in front of B. In this case, 2 students are talking about how the light curve would appear when observing the eclipsing binary system seen before, which is this case here. And student 1 says, I think that the dip in the graph is deepest when the blue star is in front, like in this case of the red star. Since the blue star is so much bigger, it would block off all of the light from the red star. All of this is true, but it would be less light than in this case, for instance. So student number 2 says, I disagree. The hot star emits way more light than each part of its surface than the cold star does. So I think that the deepest dip will happen when the cold star blocks the light from the hot star. Well, the answer is student 2 is correct. So the biggest dip is here when part of the B light is blocked by the M light. Question number 11. Draw a line to illustrate the amount of light we would see from an eclipsing binary system containing a sun-like, a G star, main sequence star, and a red giant. And we're assuming that we can see them side by side and they will be eclipsing one another. We can see that the sun is going to have this luminosity, whereas the red giant is going to have this luminosity. Also, the red giant is going to be way larger than the sun in size. So we're going to have the typical curve with 2 dips, and our role is to identify which dip corresponds to what situation. So all these 3 flat regions are where when we get to see side by side the 2 stars. And here there is some dip, but not as much as here. in this case, is when the sun is in front of the red giant, and here is when the red giant is in front of the sun. So there is a reduction, but not as much as in this case, because the sun would be blocking a lot of brightness from the red giant and replacing it by a dimmer area with the intensity of the sun. And this is the end of the lecture tutorial activity. We continue with section 11. Turns out that there is a relationship between mass and luminosity, which makes sense if you think of larger systems having more mass and larger area, and consequently larger luminosity. Well, it turns out that this can be quantified by observations. If we plot the luminosity this way and the mass this way, and then put a dot for every main sequence star that we can find, we're going to see that they all lie on this region that looks like a straight line. We have to specify that it looks like a straight line, but this is not a linear scale. So the relationship between mass and luminosity is not linear. It is linear on a log scale. You can see that this distance here is only 0.1 difference, 0.1 solar mass in difference. But the same distance here is 1 solar mass in difference. And the same distance here is 10 solar masses in difference. So this is growing, is getting larger and larger with a log scale. The same here, it goes in factors of 10, 10 to the negative 3, 10 to the negative 2, 10 to the negative 1, 10 to the first, 10 to the second, 10 to the third, and so on. So, but in general terms, we can see that the more massive main sequence star is, the more luminous it will be. So, this can help us a lot to determine the mass, approximate mass of a star by itself. It doesn't have to be a binary. So, for instance, if we measure the luminosity of a star, then we can just come here and down here, and we're going to get a very good estimate of the mass of the star. So we have one example here, a main sequence star of 10 solar masses. This is 1. This is our sun. It has luminosity 1. So, but if we go up to all the way to 10 solar masses, the luminosity is going to be roughly thousands of times larger. Turns out that it is 3,000. If on the other side we go down in mass, for instance, if we go from 1 solar mass to 1/10, then we're going to go all the way to 1,000th of the intensity of the luminosity. So 1 over 1,000 solar luminosity. We can plot the same type of information in a different way. These are the stars in the main sequence, along with their masses in terms of solar masses, in units of solar masses. So we can see that in general terms, when we go higher into the snake of the main sequence, we're going to be increasing the mass. So as we move up, the mass, the luminosity, and the temperature increases. So all of these stars are hotter, more luminous, and more massive than these other stars. And that was section 11. Now in section 12, we're going to see yet another way of looking at the orbital motion of binary stars. Sometimes in binary stars it's hard to see them actually visually orbiting one another. So in those cases we say that the binary star cannot be resolved, and we don't see eclipses, but we can detect, we can find that a system is a binary system just by looking at the spectrum. We saw before in sections 4, 5, and 6, I think, that what is the spectral analysis? The spectral analysis is telling us information about the light being absorbed by atoms on the atmosphere of the star. Some lines will indicate that there is titanium oxide out there. Some other lines will indicate that there's nothing but hydrogen on the atmosphere. And we know the frequencies and wavelengths of those lines that are missing. And that is basically what we do when we do a spectroscopic analysis. Now, if by looking at one of those stars we find both titanium oxide and hydrogen, we see that these do not correspond to one another, because hydrogen is observed whenever we have a hot, very hot type A star, whereas titanium oxide cannot survive under those high temperatures. So this one indicates that the star is a cool star, something like an M. So what is it? If we see hydrogen and titanium oxide at the same time, what is it? Is it an A or is it an M? Well, what it means is that it's both an A and an M, and it is a binary system. So also there's another way of finding out that a system is a binary system, and this is by looking at the Doppler shift of the spectral lines. The Doppler shift, this is a video that I urge you to look at on your own. I'm not able to download it, but it refreshes in your memory what is the Doppler effect. Basically, the light that is being produced by an object that is approaching us is going to have a shift in the frequency as compared to if the object that is producing it would be receding from us. In one case, we say that it's red shifted when it is moving away, and in the other case, it's blue shifted when it is moving towards us. Well, in this case, we have that effect to our advantage. We have two stars, star A and star B, and they are orbiting one another. Imagine that this one is producing, both of them have, say, hydrogen, of course. They're producing hydrogen lines. So both, at this point, the star is moving perpendicular to our line of sight. The Earth is down here. So the light that gets produced in this direction will come to us. But since the motion is perpendicular to our line of sight, then there will be no Doppler shift. So the lines being produced by the star A will fall right there in the spectrum. If we look at B, under the same circumstances, B again will be producing light that will come to us without any Doppler shift. So it's going to be there. So let us say that both A and B produce these two lines in the spectrum. Well, in the next part of the trajectory, A will have moved here and B will have moved there. So at some point we're going to have them like this, and A is going to be receding from us and B is going to be approaching us. So in this case, B will be shifted towards lower frequencies, and this one is going to be shifted towards higher frequencies, so they get displaced. So A now shows these lines, whereas B shows these other lines. Later on, they will go back to being again perpendicular in their motion with respect to our line of sight, and the lines will lose their Doppler shift and they will come back to the original positions, just like in the previous initial stage. And finally, when they are about to complete their cycle, they will be again moving this time A towards us and B away from us, and the shift will be reversed as compared to this other case. It is this displacement that will be telling us that the light that we see is not from a single star, but is from a binary system. We have this case here that shows that effect. Let me run it again. As you can see, the spectral lines are shifting to one side and to the other side, and at some point they overlap one another. If we take pictures of it, this is the way it would look. This is one case in which they have this relative motions towards us with some shift, and the lower spectrum corresponds to this other case. And we can see that without Doppler shift, we would see, say, one absorption line, and with the shift, this one would become two lines, separating the spectrum of A from the spectrum of B. And we can see it repeated over and over again in all cases. So this effect allows us to understand that whatever we get to see, whatever we're seeing, in this case is the Kappa Arietis, which is right here, is not a single star but a binary system. Depending on how fast that switch of the shift takes place, we can estimate the velocities, and the velocities, both absolute and radial velocities. And for instance, in this case, we have one star having this motion. What we see here is the radial velocity, and this is time, and the radial velocity is in kilometers per second. So it goes from moving at 40 kilometers per second away from us to moving to -20, which is 20 in the direction of in our own direction. So the other star would be doing exactly the opposite, like that. Now the fact that they are not symmetric around zeros down here means that the whole system is moving away from us. Otherwise it would be, if it were stationary, would be symmetric with respect to 0. So the entire binary system is moving away from us at a velocity of 12 kilometers per second. So right here, this is 12 kilometers per second. And if we want to represent these speeds in miles per hour, we're talking about 80,000 miles an hour. Well, this concludes chapter 11. Let's do a quick summary of the new ideas that we found. Well, we began by looking, we're characterizing stars. This is the main topic of the chapter. And one of the things that tells us something about the stars is their location in space, how far they are from us. We talk about parallax, how we can use stellar parallax to find the distances. And we talk about spectroscopic parallax. Now, stellar parallax works up to 30 parsecs or so. It doesn't work for huge distances. But this other method that we found, the spectroscopic parallax, works in a different way. And we talk also about the apparent and absolute magnitude of brightness of the star. The apparent magnitude was denoted by the lowercase m, and it tells you how bright something looks from our point of view. Whereas the other one, the absolute magnitude of the star, denoted with a capital M, it tells you the true brightness. And it is like placing the star at 10 parsecs from us and measuring its intensity. Again, the luminosity of a star is the amount of energy emitted per second. The absolute magnitude of the star is the apparent magnitude that it would have if we were to place the star at 10 parsecs away from us. And the absolute magnitudes can be calculated from the apparent magnitudes, provided that we know the distance. The temperature of the star was related to the color of, or to the spectra. And by looking at the spectra, the stars were classified into these spectral types, O, B, A, F, G, K, which can be remembered by the usual O, B, A, fine guy and kiss me, or something like that, fine girl and kiss me. And of course, all of this is nothing but the surface temperature, which is the outside temperature of the star. We talk about the H&R diagram, Hertzsprung-Russell diagram, which is a plot of luminosity or brightness against spectral type or temperature. And by plotting stars in this diagram, we learned that there are different types of stars. We call them main sequence stars, like our sun, giants, supergiants, or white dwarfs. We also learn about the mass-luminosity relationship that tells you that the mass, the larger the mass, the larger the luminosity, is not a linear relationship, but it is a relationship nevertheless. And we also look at the distance of stars, how we can determine the distance by looking at the spectral type and the luminosity classes. We talk about binary stars. 1/3 of all the stars in the Milky Way are binary, and if we can see them, they are known as visual binaries. The masses of the two stars in a binary system can be calculated, provided that we know information about the trajectory, like the semi-major axis and the period in years. And some binaries can be detected and analyzed, but in some other cases we cannot do much. But we can look at different characteristics, like for instance the Doppler effect and the Doppler shift of some specific lines will give us information about the binary system. We can also look at the variation of the intensity that we get from the binary system, because if an eclipse is taking place, we can see that the fluctuation will give us information about the period of oscillation, things like that. So there are a bunch of new words that you can use to impress your friends and family. For instance, you can ask your grandmother about, do you know what is a stellar spectroscopy? And most likely she won't know, but that will be a good start of a nice conversation. So going back to the original questions, how near is the closest star other than the Sun? Well, it's Proxima Centauri, which is 4 light years away from us. The so-called past president star, because whatever is taking place now, the radio news that we're broadcasting will reach them in 4 years. So, like they say, if you don't like the current president, you can always go to Proxima Centauri and relieve the previous president. How luminous is the Sun compared to other stars? Well, it's exactly in the middle. So most luminous stars are about 1 million times brighter, and the least luminous stars about 100,000 times dimmer than the Sun. So we're right in the middle. What colors are the stars and why? Well, we found a lot of different colors, and they have to do with the surface temperature of the star. And are brighter stars hotter than dimmer stars? Well, the answer is generally speaking yes, except that it has to do with the size also. So there are many bright stars that are cooler and larger than hotter and dimmer stars. So it depends on different factors. Compared to the sun, what sizes are other stars? Well, there are larger and smaller. We're in the middle again. So there are stars that range from over 1,000 times the sun diameter to about 1/100th of our diameter. Are most stars isolated from other stars as the sun is? Well, not necessarily. There are many, here in the Milky Way, about 1/3 of the stars are in pairs or even in larger groups. We're going to talk about the quintuplet later on. And this brings us to the end of chapter 11. Thank you.